to those of you who showed up. I'm Derek Soder. This is Ryan Perma. We're both with EI, and today we're going to talk about EI Bootroot. Why EI Bootroot? Because there's already another Bootroot out there, and do a little bit of name disambiguation. So, Bootroot is it's a survey of the capabilities, challenges, and implementation details of boot sector code that infiltrates the Windows NT family kernel. Now, this is the first privileged code to run on the processor before any part of the operating system. I mean, of course, after the BIOS. So we don't want to operate the machine. We want the OS to operate the machine. So the trick is, how can we hand back control to the operating system while still retaining the capacity for execution and also being able to insert a couple of modifications of our own? What we're going to talk about is the boot up process, specifically how it's pertinent to completing a project like this. We're going to talk about, and that includes Windows startup as well as how the BIOS hands execution to various boot media. We're going to talk about EI Bootroot, how it works, capabilities and shortcomings, and then we're going to demonstrate the EI Bootroot Kit network backdoor. Highly recommended knowledge is just something about Intel architecture, real mode, protected mode, and some about the Windows kernel. So anyways, I'm going to hand it off to Ryan to take us from boot into the kernel.
Good morning. Let me just make sure I got everything. Can I get that first page?
Oh, yes.
Got it. Okay. I'm going to be talking today about the actual boot process. It's going to give you some useful background. We're going to show a little bit of reference here to see how a machine goes from the powered off state to having a running kernel in userland execution mode. And this will lay the groundwork for how we're going to subvert this process and still maintain control of our code. Booting up is kind of a two-phase operation. We have the BIOS level, the actual hardware interactions, the specs for what's necessary to boot up, and then we have the NT process of boot up. First of all, I'm going to cover the BIOS portion here. To start out with, the BIOS is designed to transfer execution to some type of media. That media can be a floppy drive, a diskette drive, a CD-ROM, or using a system called PXE, a networked boot. There are other types of boot media like USB and things like zip drives, but we're just not going to cover those in this. Their specs are a little bit different and not necessarily pertinent to the EI Bootroot project. Once Windows starts up, right now it almost always starts up from a hard drive. That's been the history of NT, the problems in making bootable media that could access NTFS and deal with the whole NT boot process. So it starts with a booting from a hard drive. You have your hard drive master boot record that transfers control to the initial Windows loader. It's a bootstrapper that sets the process in motion. That will load NT loader, which will then load OS loader, NT detect, and then finally NTOS kernel and the associated pieces like the HAL, which is the hardware abstraction layer, and the boot drivers. And right now in our project, the boot drivers are a real key piece. So we will go through these all more in depth here. Basically, almost everybody boots up off a disk drive. In modern machines, your BIOS can select your boot order, but nearly all the time you're booting up off of a disk drive. In booting up off a disk drive, we always execute in real mode on an Intel processor, 16-bit segmented address space. On startup, the stack pointer is set to 0, 400 hex rather, and the data segment for the boot is set into 40 hex here. That's what BIOS uses for its data area. In hard drives, when they boot up, the very first sector is the master boot record. The master boot record is a table of sorts that's designed to facilitate locating other partitions and beginning the boot process. What happens is there's a small bit of code at the beginning that will, first of all, relocate itself to 600 hex. So it moves itself out of the process area that it was in so that the new code can be moved in. It creates a bootable partition from the partition table and copies that into the first area there at 7C00. The partition boot sector, it's always part of the operating system. So this is where we get our next stage of the operating system load. I'd like to show you a little bit about the NT master boot record. We got this from ntfs.com. Great stuff. Great site if you're interested in this. The NT boot MBR is a collection of information telling different things about the various partitions that you have, how big they are, where they start on the disk, and if they're bootable or not. And basically, this is a standard that's available and pretty well understood. Now I'm going to cover some of the booting from CD-ROM. This is a little bit different, but in many ways it's similar. Let's start with the differences. The sector size on a CD-ROM is actually much larger than in the case of a hard drive. You have up to 2K, where a hard drive only has 512 bytes available to it, and that will give us a little bit more sector read space. The data format is a ISO 9660. There's also an ECMA standard on it. This is a much more complex format than the hard drive spec actually is. Additionally, the spec for bootable CD-ROMs is called El Torito. This is an additional spec on top of the ISO 9660 that's specified for the process that you need to boot a CD-ROM. Now, I'm going to cover some of the El Torito spec here as it's pertinent to the EI Bootroot project. We have, this is the very first chunk of the spec. Much like the MBR, this is a standardized format. Most of the stuff in here basically has to be one way for the device to boot. There's a little bit of wiggle room and some specifics. Things I'd like to discuss are things like, right now we can cover things like sector size. Right now, though, this layout part is not super important. Most of this is all leading to a more specific piece. This is another expansion. We're covering things like the volume descriptor and the spec version. The real important one here is located in the boot record volume, and that would be the pointer to the first sector of the boot catalog. The boot catalog is much like a boot partition in the MBR, and that's going to be our focus. The third part here is actually the boot catalog. We're covering a lot of very important pieces to tell us really how to boot. It's akin to a boot up partition. What we have is the type of media, the platform ID, a lot of important stuff. Right now, we we actually, because BIOSes do not necessarily support the ISO media in full, what we do is we actually emulate a hard drive or a floppy drive using interrupt 13 writes and reads that the BIOS is very familiar with. The piece that we have here, the boot media type, will specify whether we're actually emulating a hard drive or a floppy drive. This is so that all BIOSes can actually boot on this spec. Additionally, really important things here are we have the load segment. In this case, we're loading on segment 0. We have the sector count, which is the number of sectors that we're going to be, actually be loading for our boot, right? And then we have the load RBA, which is the exact start of where to load our code here. So all of this is basically leading to, we have network boot here. I'm missing a slide. In the network boot, this is called PXE. PXE is a pre-boot execution environment. It was a spec that was developed by Intel. It works with the local Ethernet driver to remote boot things like diskless workstations, and pretty much any modern motherboard will support the PXE standard. To do PXE, you need an outside server that's going and a network, and this server is going to serve as a boot P, which is kind of a precursor to DHCP, and then TFTP to serve the image. We have, in a normal situation, you boot up, your PXE driver on your BIOS will request an address over boot P, which is very similar to DHCP, and it will receive not only an address, but an IP of the host to TFTP from and the name of the image that's going to TFTP. So once it receives that address, it's going to request out and gather that TFTP image, load, and operate on it. Basically, the TFTP, as we know, runs on UDP. 69 is a pure UDP port, and you do need to be running a TFTP server for this to work. In the boot process, again, this is very, very similar to booting a hard drive, where we have we start execution at 7C00, exactly like a hard drive. The difference is that in our TFTP load, we can pull down about 500K, which is typically bigger than we have in most situations. We really don't need that much, but it's available if necessary. One thing that we've noticed in loading and playing with this is that PXE, unlike normal hard drive boots, the initial registers are sort of undefined. They're kind of left in an odd state. So if you're writing an image that you need to PXE boot, make sure that you clean up all your registers and set them to where you really want them to be. This is basically a quick back and forth on how a PXE boot actually works. It's just a simple packet dump, just showing the kind of communications that are happening. First, the client boots up. It has no IP address. It issues a DHCP discovery to get its IP, and your DHCP server, which in this case is a PXE-based DHCP and boot P server, will respond and say, hey, this is your IP. This is going to be what you get, and this is the host that you're going to get it from. The actual request comes back, and we act the request to validate the DHCP transaction. And then, again, as part of this DHCP, some of the attributes are the various things like TFTP host and file name that you're going to download. With that established, the PXE client that you're booting from will make a connection to a TFTP server. The TFTP server will then feed you the file that you have, so it's a straight back and forth downloading TFTP. Once the file is actually finished downloading, execution can begin. Now I'd like to actually cover, now that we actually have our media and our boot image, all this was leading up to a single thing, which is to get to how Windows is going to start up. This is all specs and real low-level stuff that is important, very important, but standardized, and there's not a lot of wiggle room there. Now we're at Windows land, and this is where the heart of where EI Bootroot comes in. The Windows startup, the very first phase, is a bootstrap loader. This is a very small chunk of code that's whole purpose is to get the ball rolling, so to speak. The very first thing that it does is it acts sort of as an unpacker. Because of the limited amount of size that you have at this level, you need to, and the length that Windows is going to, the very first thing it does is it loads the first 16 sectors, 15 additional sectors at ODOO sector on 000. We're still in real mode here, so we're working a segmented address space here. One thing to note is that the Windows partition or the Windows bootstrap loader actually makes use of the IBM Microsoft Int13 extensions. These are sort of known as like LBA extensions. They're designed to handle very large disks. So anything, I believe, over 137 gigabytes around there, it's necessary to actually use these. And Derek will get into a little bit more on this a little bit later in relation to Bootroot. We do then, once this is up and loaded, we pass on to the next chunk of our bootstrap. Now we focus on loading the NT loader. NT loader is the first very visible piece of NT as you're loading. We load this at 2000, and because we're still in real mode, we're in a very limited execution environment. We literally are not offering any additional services to NT loader, and this is all being loaded into that 16 sector space that we have. What we do have is that in that 16 sectors, we're actually only using, or NT is actually only using around 40% of that, meaning that 60% is just idle space. They could have got away with allocating 8 sectors instead of 16, but I guess they decided better safe than sorry. What we found is that actually gives us some pre-allocated space that could be very, very useful for code that we have. Now, NT loader. We're beginning on our path to actually being a Windows machine at this point instead of just a simple Intel BIOS boot box. This is the first time that we enter protected mode. We're still in 16-bit, but we are now in protected mode. For that, we create a GDT, an IDT, and we use these throughout pretty much the rest of the low-level Windows startup. Another function of NT loader is that we will wrap various interrupts inside of protected mode so that we can offer those services down the line. We'll do things like video, disk, keyboard. The one that we're using a lot is disk. Much like in any interrupt system, these are passed down to real mode from protected mode. The next stage is OS loader. Now, OS loader is actually embedded inside of NT loader. It is a full PE file, although it's slightly munged before Windows 2000. It's missing its MZ and PE header. Basic reverse engineering tools like IDA can still process it, and you can learn a lot by looking at what OS loader is. For the most part, because it's embedded, you don't really often see the OS loader, but it's wholly possible in different versions of NT to actually have that out there. What we do then is that in this NT loader, we drop the OS loader, and then we execute it in 32-bit protected mode. So now we're finally in the flat 4 gigabyte address space that NT itself will run inside of. This is a quick rundown of the GDT that NT loader's using. This is the GDT that you're using across the board through the startup process until we're basically Windows at that point. Kernel hackers should take note of this. We have things like our Ring 0 code data, Ring 3 code and data, and a variety of other pieces that are very similar to normal kernel, although we're in 16-bit. We're using 16-bit segments here. This is mostly for reference, so you might want to just check your slides on the book. What we have now is we're inside of OS Loader. OS Loader is doing the first chunks of things that you would normally see inside of NT. Things like the boot INI that have been around and dictate the loading behavior of NT are all available and processed here. It'll read that file in and cache the results and use them throughout its process. One of the first things it does is execute ntdetect.com. Now, this is a real mode application that the purpose is to determine the underlying HAL and the underlying multiprocessorness of the NT system. It gives it information on which NTOS kernel and which HAL to load. Additionally, we enable paging. There's a boot INI option to handle a 3 gigabyte user space that's processed and added here. We set up the typical virtual addresses available for the GDT, IDT, and the page tables. Again, this is how the kernel will begin to reference this stuff. From the NTDetect, we will load the appropriate HAL and NTOS kernel. HAL is a hardware abstraction layer. Various underlying hardware, Compaq, HP, Dell, that uses specific chipsets will have different HALs. And multiprocessor systems typically have different NTOS kernels. So you select based on the NTOS detect, and we load them and import any of the dependencies. There are some like the boot video and whatnot that need to be loaded for continuation of the boot process. We load them at their preferred base addresses and then map them to the appropriate virtual addresses. Additionally, OS Loader will load the registry, which is actually just a file in System32 config system. It loads that and maps it into memory, so now the registry is available for further boot processing. Finally, it loads the NLS code pages and Ricard fonts. These are like text space and Unicode font, character sets that you will use if you're doing Unicode text processing and stuff. Next up, we have the boot drivers. Now, this is a real important part here. We actually will create a list, or we'll process the types of boot drivers. Now, these drivers are set up in the registry as a type 0, which indicates that like services, they start up at boot time. Drivers happen before services, obviously, and right now we create a PS loaded module list, which is a familiar kernel structure for loaded drivers. It also mirrors the type of structure that userland PS API and various other module list utilities from Microsoft would do. It's known as the BL loader block. Next up, or just one thing to note here rather, is before Windows 2003, there was no actual alignment of these boot drivers. They just would load, and they may not have been on a page or on a 64K alignment. They're just simple file mappings of the drive. So right now, basically, we're selecting the boot drivers and file mapping them into memory. We do not, at this point, execute the boot drivers. Our purpose is to get them into memory here. So now we go to NTOS kernel, which is NT proper, as most people know it. And NTOS kernel and HAL are very tightly integrated. They provide most of the base services for NT and for subsequent pieces. So the boot process kind of goes like this. The NTOS kernel will select, first of all, the TSS, IDT, and GDT and take control of it. At this point, NTOS kernel is there to stay, and it's going to control this from now on. We then initialize the processors through the HAL and add ABIOS support that will basically set up the processors so that we can continue forward. There may be one or more processors. The final thing that we're going to do is we're going to initialize the various kernel subsystems. And in NT, there's a lot of kernel subsystems. And in this situation, they actually, although there's actually 3 phases, one of them is much, much, much less important and totally unimportant for the EI boot root talk. Phase 0, basically, it's a first pass. It's not worrying about dependencies. It's just going through, firing off a bunch of calls, setting up a bunch of subsystems on their very base level. It calls into KI system startup, KI initialize kernel, and then finally into EXP initialize executive. Phase 1, and I'll cover more of these in depth here. Phase 1 is the actual initialization phase that does a variety of startup sequences and mostly comes down to the actual initialization code. Basically, it's in a separate system thread. The boot drivers are executed at this point, so the driver entries and they're set up and now operational. And then finally, starts up user land by executing SMSS. Phase 2 is the phase that I was mentioning that's not really important. It mostly deals with licensing between Windows Server, Windows Workstation. It's really just not important for boot root. It does execute, but it doesn't really control any flow. Covering phase 0, we have a fairly simple call stack here. Basically, the HAL will initialize the processor first. It will cover basically setting up spin locks and registers and everything per processor. We'll go initialize the kernel, which will set off a chain of events. We'll cover the init system, which we cover the service descriptor table and the descriptor table shadow, which NT kernel hackers that do any kind of hooking are very familiar with. We'll initialize the process for what will eventually become the idle thread. So basically, we create this process and this thread, and this is the thread that runs in the background at all times, just running as idle. Finally, we're going to attempt to initialize our executive, which is the NTOS kernel, the heart of NT. Again, since this is phase 0, we're just kind of doing a shoot-through on this. We'll hit the HAL and initialize some data structures there, and basically walk through things like the executive init system, the memory manager, the object manager, the security manager, and then basically the PS init system is the one that actually spins off starts the idle thread here. Phase 1 is the actual heart of where everything's happening here. You see a lot of redundancy here. We're actually shooting through a lot of this again to take care of interdependencies in these startups. So we go through, we init the HAL again that covers things that we missed last time, init the system, object manager. Basically, we go down the point. We cover LPC, which we didn't before, and then we start. We fire off the phase 2 initialization, which is the licensing piece. The key part that we want to note here is down here at the bottom. We have IO init system. Basically, IO init system is the code that actually will run the driver code. This is hit the driver entry and load the boot drivers into memory, they're loaded into memory, it will actually execute them. Additionally, it covers things like loading NTDLL, which is a core kernel of functionality inside the kernel. Additional things like a init system is hit another time to create an executive page table that the kernel uses. We have PS init system the last time will actually reallocate or export of the NTDLL. One thing to note here is that before this last piece, in fact, when your boot drivers load, you do not have actual access to NTDLL, so your boot driver may not have access to any exports that traditional drivers usually do. That can make it a little bit more hairy, maybe force you to roll your own, as it were. Finally, the RTL create user process, SMSS, is what launches the userland code, and now we are a Windows system, basically. You can, at this point, do things like log into it and begin to go forward. Derek, I don't think syskey will cover that. Like mostly syskey is going to deal with like this sec.
We'll get to it at the end. We got to try and make sure that we're on schedule to actually by the time everybody's started. We'll certainly cover that. I'd like to actually pass it off to Derek here, where we're now going to go into boot root proper and show the magic, as it were. Cool. So Ryan's laid the groundwork. Now we're going to use this reconnaissance to plan our invasion of the kernel. Our problem with EI bootroot is that we got too much control and we have it too soon. Kind of a funny situation to be in. We want to give almost all the control back to the operating system because we want it to do its thing and appear seamless to the user. The user wants Windows. They don't want EI bootroot OS. We don't want them to know that anything has changed, but we do want to change a couple things. Giving control back to privileged code is tricky because this privileged code can take over the entire machine state and basically ruin our chances to regain execution. So these are the advantages and disadvantages of being at this specific point in between when the BIOS hands off execution to the boot medium and stuck before the operating system. So let's see what we have to work with when our code is executing. It's a pretty barren landscape. We have all memory, we have all the hardware, everything on the processor. We pretty much have everything except the operating system, which is still on disk. There's no OS code to patch. There's no OS data structures to modify. We do have a couple BIOS established data structures. We've, of course, got the interrupt vector table. We have the BIOS data area, which Ryan had mentioned, at linear address 400, segment 40. Ralph Brown's interrupt list contains a file memory list, which goes over that in great detail. Recommended reading if you haven't read it already. All right, laugh it up. No, let's see. So 640K conventional memory. There's, of course, more memory on the machine if you want to go into protected mode. There's probably also a BIOS interrupt, like interrupt 15 service that will let you access protected mode memory, or the higher memory. Of course, all the CPU registers, keeping in mind that Windows will blow away whatever we put in most of these. But, for instance, we have the debug registers. It's kind of an interesting idea just to play with, that maybe we could set something in the debug registers and perhaps Windows wouldn't initialize them so that at some certain point in Windows startup, the setting in the debug register would cause us to regain execution. Problem with that being that it would throw an interrupt, and Windows has taken exclusive control over the interrupt table, but it's just a random thought. There are other processors on the machine and multiprocessor machines that we could use. That'd be kind of neat to have another processor running simultaneously doing these kind of real-time modifications to the boot environment. It's a little bit James Bond. So here's our plan. We know what we've got to work with. Now, and we know that Windows is going to inadvertently try to evict us by taking over the machine exclusively. However, it does still have to trust the BIOS, and that's our angle of attack. It has the interrupt vector table exposes the interrupt services that the BIOS provides, which is kind of like an exported API in a way. These are all services that the BIOS is providing to the operating system to get itself started with. So what are we going to do? We're going to modify these structures. We have the interrupt vector table. We have the BIOS data area. They're all accessible. They're all universal, well-known offsets, and of course they're writable. Obviously the BIOS is not writable, although I'm sure there's some people in there who would disagree with me. But we didn't want to try and flash the BIOS. That would be very difficult to debug. So we're going to function as a BIOS hook and use that leverage to invade the Windows kernel when it appears. More specifically, our solution is first to go resident. We have to carve ourselves out a niche in memory where we can hide and not be tampered with. Because Windows is taking over every other aspect of the machine, it's going to take the memory too. The way that boot viruses have done this forever, which is a good sound technique, is to take the amount of conventional memory reported in the BIOS data area and just kind of shave a little bit off of it. This allocates some memory at the top of conventional memory that will never be touched. This count of kilobytes of conventional memory is respected by all memory checks. So once we've gone there, we can hang out there forever and not worry about being modified. Next up, we copy ourselves there first thing because we want to get out of the way. Right now, as Ryan pointed out, we're at a specific linear address, which is where all boot sector code expects itself to be. We're there too. We want to get out of the way because what we want to do is load the hard drive boot, the master boot record, and execute it so that the execution seamlessly transfers to the hard drive. So say if you left a CD or you left a floppy in the drive, just kind of inconspicuously, and somebody booted off of it, it would just pass execution on through the hard drive, and no one would be the wiser unless they're looking at the little green LED or listening to the noises that your computer makes. What we do after we're there is we hook interrupt 13, the disk interrupt, and we're going to scan the operating system as it loads, sector by sector, looking for a specific code signature. And we're going to patch at that code signature and essentially virtually patch the operating system as it's pulled off the disk. Windows startup, of course, depends on this interrupt as its only means of disk access until it's loaded the disk drivers, etc. So it's forced to trust it. And our code has first dibs. There are, of course, other things that we could have done. We can modify the operating system files on disk. That requires us to understand the file system. I guess it's kind of the obvious solution, but there is already existent code to read the file system. For instance, in the Windows bootloader that Ryan was talking about, it already understands NTFS, and it's at a location that we know and can get to. So we could perhaps piggyback off its code and kind of save some of our own space, because our space is on a premium here. Excuse me. Yeah, we could have also, really doesn't relate to infiltrating the kernel. It's just kind of a neat observation. There's an interrupt, int15, a specific service that will give the operating system a memory map of what memory is reserved and what memory is actually available. If we hook this and we filter the results passed back to the OS, then we can make physical memory disappear. It will not be accessible. It will not be used by Windows. It will not be accessible via device physical memory. The only way to get to it would be kernel code that goes and tweaks with the page tables. So it'd be kind of a neat place to hide stuff in memory. However, you've still got to have some code that's visible in virtual memory in order to go map in and access this hidden physical memory. So there's still a little stub of code that could be detected, but it's just a thought. There are probably other interrupts that we could hook to regain execution, and perhaps much later in the operating system startup, after OS code and OS data structures are present for us to modify. We didn't look at it in too much detail, but one of the problems is that these interrupt handlers that we would install run in real mode, and all the operating system stuff is up in higher memory, outside of conventional memory. So we would need to enter our protected mode ourselves to get to it. It's going to cost us more code bytes in our boot sector code, and just a little bit messier. So it's something that we could do, we just didn't do. This is that system memory map I was talking about. As you can see, the second blue line, the one with 7DFOO in the right column, is the big one that tells how much, basically all the unused memory up above conventional memory, the video BIOS, the reserved conventional memory, etc. If we chop this value down and we filtered out the other ones that are reclaimable and available, then we could actually lower the cutoff to make it appear as though the machine had less physical memory. So finally someone implemented it. These are some of our ideas on how to implement it, and here's where we put them into practice. EI Bootroot Kit is a proof of concept for the EI Bootroot technology. It's not really a traditional rootkit. It doesn't hide things. It's just a network backdoor, but a network backdoor that lets you run kernel code through a firewall. So it's ups and downs. It loads from a variety of bootable media. In particular, we're focusing on floppy disk and CD-ROM drive and network boot. It does exactly what I just talked about. It reserves some conventional memory. It hides up there. It hooks int13 so it can monitor all sector reads. It lets the read occur, and then it looks through the disk buffer that was filled by the BIOS for a specific code signature. If it finds it, it modifies it. The code signature we picked is in OS Loader, which, as Ryan mentioned, is a part of NT Loader. And this, we choose a special location that is after all the boot drivers have loaded, so we can find indis at this point, and we can go hook indis.sys. That backdoor inspects all received incoming Ethernet frames, looking for a specific signature in a specific place, and then runs code out of the packet if it's found. Features. It works on Windows 2000 and later. It does not work on NT4, to our chagrin. We need to work on that. We don't want to be negligent. We just hadn't got it working yet. And it fits into 512 bytes, so one sector. So that means our code doesn't have to go load other sectors off the disk. So we squeezed it to make it fit. Of course, this idea is simple, hijacking the boot sector and running our code, but the devil is in the details. So we're going to go over some of those complexities here so you don't have to. Here's the more granular play-by-play. First off, we move ourselves to reserved conventional memory. There's that word in the BIOS data area that we just subtract from, and then the final subtracted value is actually, we multiply that by 1K, and that's the address that we can hide at. We shouldn't, when you're copying yourself from the initial load address at linear 7C00, you shouldn't assume the value of CS. This was an early mistake we made. And the reason is because when you boot from a CD, it puts, the segment is different than if you booted from a disk. The linear address is the same, it's just that the value in CS is different. And if you make any assumptions on that, then you will fail. The int13 hook, as we talked about it, it looks for reads and then it scans the disk buffer that was filled with the contents of the disk. Specifically, we're looking at two read services. There's a standard one, AH02, and then there's the IBM Microsoft extension, 42, which is required on large disks. One thing, a little lazy shortcut we tried to attempt is looking for the installation check for those extensions and just responding with failure, saying those services aren't available because we don't want to support them. That causes the operating system not to load. So we do both. It's not a big deal. It's just a little bit different. All the details are in Ralph Brown's interrupt list. It's good stuff. You should check it out. And it's not that bad to support. It doesn't cost us much in the way of code bytes. We still got it in one sector, so it's all right. The signature choice is extremely important. It needs to be unique. You don't want to go patching random pieces of the disk as they load. You want to patch exactly one piece of the operating system when it loads. It should, of course, be cross-version. Ours is 2000 XP and 2003. It's probably not NT4. That's my best guess as to why we're not working on NT4, because the signature is just not there. And it needs to be not split across the sector boundary. If half of the signature is loaded in one sector and half in the other, our hook is simple, it's dumb, it's stateless. It's not going to realize that that was loaded. Of course, it would also be tricky to patch the signature in two places, but so just choose one that's not split across sectors and do yourself a favor. Another little caveat is that OS Loader checks checksums on the modules that it loads. It does not check the checksum on itself, so that's why we target it to patch. We were originally patching Indus directly or NTOS kernel just for fun, and they're all checked. So you could disable the checksum code. That was one thing we did, but it's just more wasted space in your packet. The best way is just to attack OS Loader itself and then use that as a jumping off point after the modules are loaded and after all the checksums are verified. Here is the specific place that we patched. There are 7 bytes here just to make sure the signature is unique and easily identifiable. However, it breaks an instruction boundary. We got 1 byte of another instruction in there, so that's no good. Therefore, we went with a special kind of hook. We wanted our hook to be absolute because this is a situation. Our int13 hook sees the contents of the disk in the disk buffer. It doesn't know where the data is going to end up eventually. It's going to be copied off into higher memory somewhere. We don't know where. We don't care to go find it. By making our hook absolute, we know our address, so we can use an absolute hook to get there from absolutely anywhere. The most obvious absolute hook is just call segment offset, which is 7 bytes. That's a little too big. So we went with the 6-byte one. It's just a call memory. The memory address that we call is absolute, and then the pointer at that address is absolute. So it's still an absolute hook. It only takes 6 bytes. It's just the best choice for the situation. Paging is not a concern in this case. OS Loader will implement it, but it doesn't matter because the low 16 meg of physical memory, which is definitely where we are, is mapped as a low 16 meg of virtual memory. So we don't have to worry about that at this point. Here's what our OS Loader patch function does. We installed the the hook. It's going to jump back into our code. Our hook function is going to scan through OS Loader for the loaded module list. This is the easiest way that we found to find Indus. What we were doing previously was scanning through page tables, looking for allocated memory, and looking to see if it was Indus. That's just kind of a pain. This is actually easier. Of course, our hook is a call. So we have on the stack a return address, which is our hint into our pointer into OS Loader. Now, it's not to the beginning of OS Loader, so we actually want to start from the start so that we can find our BL Loader block, no matter where our hook was called from in OS Loader. We assume that it starts on a 1 megabyte boundary, so we just round down. Nothing too sophisticated. And we look for this signature, which is after all the modules have been loaded. It's very unique and specific, not split across sectors. And it's got a pointer to BL Loader block right there. Now that pointer, you can just dereference that a couple times, and you're at the module list. We searched this module list for indus.sys. The name is in Unicode. Don't depend on the case. Don't assume it's going to be uppercase. You can be lazy, just don't be that lazy. This is the format of that module list, which is actually, I don't know if Robert's here, but sorry, Robert. He pointed out that this is the exact same format as every other module list. Kernel, userland, they're all the same. So those question marks just represent an unused field. But this is the kernel hackers might recognize this as PS-loaded module list format, which is a good way to find modules when you're already in the kernel. OS Loader passes the same format to NTOS kernel. So now we've got our OS Loader patch. It's found NDIS in the module list. Now what? We want to hook NDIS. How we do that is yet searching for yet more signatures. We have another specific code signature. We didn't have a code signature for ETH filter DPR indicate receive packet, hereafter referred to as that function. But we did have one for its caller. So we find its caller, we follow the call, and then we find that function. Now the problem is, as Ryan pointed out earlier, before 2003, the sections in the module aren't aligned to their in-memory addresses, which is actually different from the in-file address offsets. So prior to 2003, but not on 2003, we'll need to perform translation from this RVA to follow the relative call, and then translate from that RVA back to an offset within the loaded image, and in order to find that function. So we kind of had a hackish way of checking if this was the case or not. The loaded module list contains the size of the footprint of the in-memory image, and if it's a 64K multiple, we assume it's been all aligned and everything. It's 2003, it's all good. There's also a possibility that we're unlucky and the file contents really are a 64K multiple, in which case we will fail. But that hasn't happened so far, so it's good enough for a demonstration, right? If it's not a 64K multiple, it'll probably just be some 4K multiple, and that will mean that it is the file contents loaded into memory. It is not yet aligned properly. So our hook of that function stores a relative jump at the beginning, just like any other standard function hook. We know the instructions we want to overwrite because this is a well-behaved function. It uses an EBP-based frame. A little landmine is that move EDI that XPSP2 introduced. We want to skip over that if it's present so that we can overwrite the instructions we intended to. We always assume those are going to be push EBP, move EBP, ESP, just a standard prologue, and then subtract something from ESP. We don't really care what, because it is an EBP-based frame, so we can just subtract a lot, and that will be good enough. And we don't have to bother ourselves with the particulars. Write protection is not yet enabled, so we can modify the code to our heart's content. And what we need is a place to store our little backdoor function, because at this point, now it's the kernel that everybody knows and loves. Our conventional memory is probably not present. I mean, it might be, but there's the 3 GB option, and there's just kind of all kinds of circumstances where there's really a better way to do it. And this is what we came up with. It's a very small function, the NDIS backdoor. So we stuff it up in this program cannot be run in DOS mode code up right after the MZ header. There's 64 bytes there at least. It's more than enough room for our function. It's all good. This function provides remote kernel backdoor. And here's how it works. It checks the arguments to the function. It finds the Ethernet frame in memory. It finds the size of the frame. If the frame's big enough, it looks for the signature at a very specific offset. This offset is arbitrary, but it was chosen to make sure that it'll be within the data payload, even if there's some IP options or some TCP options or whatever. So, we may have to shift around our data payload a little bit, but we shouldn't have to, store anything in the headers, because that's a mess. If the signature is present, we just run the code that follows it. Now, obviously, the size of a frame is limited, so if you want to send a really big remote kernel backdoor payload, then we recommend smaller payloads and kind of copy them to a staging area. The perfect staging area is shared user data. It's at a universal address in kernel and also in all userland processes. So that's really handy. Of course, it's writable in the kernel, so that's a must. And there's plenty of room there. So it's a good place to store our payload. Now the fun part. What you've all been waiting for, we're going to demonstrate. We're going to demonstrate on a VMware from a floppy and from a CD. We were going to do network boot. I'm sorry, we had some technical difficulties. Our crossover cable doesn't work, etc. So, hey, I didn't make that cable, all right? That's not my fault. Did anybody come see the eReap talk last year? Anybody? It's an inside joke. Is it? Oh, okay.
Yeah, guess swap it.
Sweet. Oh, that's too bad. I had it in CRT mode. Nice. So there we go, VMware, everybody's best friend. What we're setting up right here is a virtual floppy drive. This laptop doesn't actually have a floppy drive, so that's why we're doing it in a VMware. Now, the thing, because the format of a floppy drive, floppy disk is so simple, we can actually just compile the assembly code and then just pass it in directly as a floppy image. Works great. So that's what we're going to do. The CD-ROM drive is not enabled right now, so it will just boot off the floppy drive. And what we have here is the host-only networking in VMware. So we're going to netcat it, our evil little packet. Oh, I'm sorry. Watch the up left corner. Just a second. See that blue smiley face? Ownage. It was a little debugging artifact, but just didn't have the heart to take it out. So if you ever see that on like your system at home or something, take that that EI boot root CD out of the drive. I guess while it's doing that, we will get ready to netcat. What I'm going to do here is I'm going to send a UDP packet. That's just what we've set it up to work with, the size of the UDP header. We're going to send it to this machine over our host-only imaginary network. We're going to send it to a closed port. It could be a firewalled port. It doesn't matter. Indis will see it, therefore we'll see it. Oh yeah, another apology. We had kind of a cool demonstration. It was just a hokey little text mode thing, but I kind of liked it. Turns out it actually doesn't work on this version of VMware, so we can't do it today. However, we're still going to make it painfully clear that we're running code in the kernel, and even to show you all a little something secret to make up for it. What is it called? Demo RSOD. Okay, so this is just the compiled stuff with a little bit of padding to get the data to the proper offset, that offset 55 that we're looking at in the frame. So here we go. Watch that VMware. Whoops. It's like a blue screen, but it's not. It's real simple demonstration. All we did is we just patched KBugCheckEX to do red fill instead of blue fill, and then threw an invalid opcode to make it happen. Anyways, please bear with me while I operate the computer one-handed. This is a special treat right here. We were not going to debut this publicly, but our little demo failure didn't give us a choice, so we're not going to boot off the floppy drive this time. We're going to boot off the CG drive. Uh-oh. What is this sysrequest business? What does that mean? What is this guy doing? There we go. I'm going to boot off the CD now. Oh, shit. Is it working? Are y'all curious? Probably not. But we're going to do it anyway. So watch that up left corner again as the starting bar fills up. See another blue smiley face. Bad sign. Well, look at that guy. What's going to happen when I boot this computer? Well, nothing's going to happen. It's just, it's just Windows. Don't be alarmed. Nothing to see here. I do like how Windows XP boots much faster than Windows 2000. It's in no hurry. I know y'all are. We're almost there. Thanks for bearing with me. At least the demonstration is working. I shouldn't have said that. Now we're jinxed. Now this is difficult to do two-handed, but I'm going to attempt it anyways. You want to? You do the honors? You have to use that Shift, Control, Assist Request. You have to use the function key, man. It's a blue one. Check this out.
I held it down a little bit too long. But.
What? Wait, what is this? I thought we just, we're at the login screen a minute ago, and now we got these shells all over the place. What's going on? Oh, no, it's not, is it? Come on. Does anybody have anything they'd like us to attempt to prove that we're running a system? Regedit, security directory. I don't have anything cool like uname or who am I or whatever. Give that a try. Do a set or something. Just do a set, yeah. Default user. Huh.
Default user. This is pre-login.
Yeah. Kind of. Go ahead and. Oh wait. Yeah, I've got a different password on this one.
How about the same?
Yeah, that's a good call. You're not supposed to be able to do that.
Did you have a different user? Let me close some of these.
All right. Actually, I got one thing I want to do real quick.
Let me just leave you alone.
All right, thanks, man.
Slow that down.
All right. Net user. I forget how this command works. / add. There we go. Net user ei in the hizzy / add ei in the hizzy. Huh. Well, I'll be. So back to the slides. We do have a little bit more material. It's not all just smoke and mirrors here. So things to do. There's always something to do. For instance, we should adapt this to more traditional rootkit functionality, like actually hiding things. We should explore other methods of retaining the potential for execution and infiltrating the kernel, besides just hooking int 13. It's simple and effective and boring. We should investigate bootable USB storage, and we should get this working on NT4. There's probably other stuff, but it's just not listed here. Bonus material. I'll try to speed through this. Just a little something extra. Did you know that you can perform a raw disk operation without being in the kernel? It's not a vulnerability. It's IOPL. It's a feature, not a vulnerability. Now, protected mode, part of the point is to keep user application code from messing with the hardware. So now there's a field in eFlags that will let user application code do just that. It's the IOPL field. It's a 2-bit field. It says the numerically greatest, least privileged, in other words, privilege level, that can do these I/O instructions. There aren't many of them, but it's enough. In, out, CLI, STI. And now only ring 0 can modify this field, but obviously because we're talking about this, there are some user threads that run with IOPL. And as a matter of fact, they're in CSRSS prior to Windows 2003. These threads are just running with it that way, and they can be hijacked through all the usual means. Set thread context, Q and APC. You want to just like write process memory into CSRSS. You find a CSRSS vulnerability. Now that's going to give you system anyways, but this is just That's why we don't classify this as a vulnerability. It's just a little half step up that you'd probably be able to do anyway running a system, but it's just a little bit sneaky. You can also ask for IOPL with set information process, process user mode IOPL. Either way, you do have to be system because that requires TCP privilege, so you might as well be system. And not really a vulnerability. But it's going to be a thorn in someone's side. It allows, for instance, low-level disk access using only I/O. For an IDE drive, and there is code out there that does this, you can use purely port I/O to read and write sectors. I saw some viruses that tried to do this. I couldn't get them to work, but this code that we refer to in references works great. This does not require DMA, it does not require IRQs, therefore it does not require you to tweak with the IDT. So pure port I/O. So what? Well, perhaps if there's antivirus on the system that's looking for, say, device physical drive access, you know, trying to stop you from changing the boot sector or doing low-level disk access, now you can get around that from user mode. Nobody, as far as I know, anticipates this. You could perhaps evade system integrity assurance software that tries to keep you out of the kernel because now you have access to the raw disk contents and maybe even some other possibilities that we'll just barely look at next. Perhaps you could defeat machine state preservation software that tries to preserve the file system and registry and restore it to a known good, like after you reboot. And it's a cool way to install EI boot root kit on a hard drive. Maybe it could be used as a local kernel backdoor. I have not written any code to do this. I don't know anyone who has. But DMA supposedly has provisions for memory-to-memory transfers. That'd be pretty neat. If you want to be like a little bit sci-fi, you could try and reprogram the interrupt controller. You could redirect an IRQ to one of the exception interrupts. Now what this is going to do is the OS exception interrupt handler is going to expect an error code to be pushed by the CPU. Being an IRQ, there should be no error code pushed, so perhaps something will go haywire and maybe just magically we'll run some code. Of course, you can modify arbitrary disk contents. That's the that's the more banal solution. We can force a violent reboot so there's no chance to detect our modifications. And the benefit here is that this is much harder to monitor than any of the other ways of getting into the kernel so far. Obviously, loading a driver, that's stop number one. It's harder than device physical memory. And ZW System Debug Control, which a guy, randnut at hotmail.com, pointed out some time back, should be harder to monitor than that. I don't know if anybody monitors that. It's just a thought. Well, looks like we're winding down. Here's some references. The things I talked about, they're all in the slides. Hopefully the print's not too small to not read. But that's about it. Does anybody have any questions? Okay.
When you load boot drivers, that they come up in like an unknown order, except for in 283. Is there any way you can take that to try to force or
You mean like I guess we could modify the registry at thanks, Ben. I guess we could try and modify the registry and maybe set ourselves as a dependency of that boot driver or something. Or what did you have in mind?
well, just like standard, because I think it always mounts it sort of at a random order. I was wondering if there's no way you could use like how it's loaded when you look.
That's a good question. I'm not sure why it would do that, and I mean, I know what you're talking about. I think I've seen it. Off the top of my head, I don't have any way to leverage that or make use of that, but it's an interesting observation. The more we know about the boot process, the more evil things we can do. I mean, it looks like they tightened some bolts here and there. I didn't really stumble over anything except for the OS loader being in a different base, the OS loader having like a full MZP header, and the modules being aligned by OS loader. These are just things that we stumbled into because of what we were trying to implement. I don't know what else might have changed. And by the way, all those references are from Windows 2000. So like the GDT or like the whole kernel, INTOS kernel initialization, all that could have changed. We just looked at 2000 because 2000 is cool-ish. Any more questions? We have CDs. A valid question is, can I have a CD? So we will be giving away the code. Maybe not right now. I'm going to use it as a bargaining chip to try and get some free drinks or something. But anybody else? I'm sorry, I'm not familiar with syskey. I don't know. I'm not able to answer that. Do you do? Okay. It's all yours.
As far as the syskey goes, that's actually a registry change to harden the SAM. So what's happening is that will almost all be in the SE, the security init. And yes, it does change it, although it doesn't change it for the scope of what we're doing. For most of what we're doing, actually, that's actually an interesting concept. I guess I never even thought about. I know that syskey level 2 is the one, or is it level 1 that just encrypts the SAM? Gotcha. I actually have no idea. I don't think we've actually tested it with that. In its heart, it would probably be just another layer, because at that point, because they can do it, we can do it too. We're just there. It's just probably more hoops that would have to jump through. We didn't really do any testing with that. So because it's all there, I would assume that we certainly could. Of course, it's much harder to convince somebody to be booting when they're typing a physical password in, unless you can silently slip a CD in their drive without them noticing. So in that case, like just strong monitoring of where you're booting from, which would probably be inherent in that, would probably prevent these types of attacks. So as far as the technical side, they're all hoops that could be jumped through.
Actually made me think of something. That made me think of something kind of unrelated, is that because this can be done over network boot, this could be done by a purely remote attacker. Wake on LAN kind of creeps me out a little bit. Now, this means that the remote attacker would have to know the MAC addresses of shut-off machines, but then he could perhaps knock over the real DHCP server, install his own, and then wake up some machines to come run his code, all from wherever, his mom's basement or something.
Or Palm Pilot.
Or a Palm Pilot.
Yeah.
Anybody else? CD? One left? He wants the CD. He wants the CD. Yeah.
Deathmatch.
The guy in green with the coffee right there, Ben? No, he raised his hand first. He's got dibs. There's more where that came from. Well, I don't know if anybody has a burner, but if anybody does have CDRs, you got a burner?
Yeah, I got a burner. I don't have CDR.
Okay. I'm sure. Come on, this is Black Hat. Somebody's got to have a CDR. What's up? Oh, hey, what's up, man? That's cool. Well, yeah, I mean, the more the merrier, you know. Just don't accidentally leave it in your drive when you know. Oh, I got one last special treat for y'all. Gotcha. Thanks.